Okay, let's start class. The first lesson is to briefly introduce machine learning and the basic concept of deep learning. I will talk about a story totally unrelated to Pokemon. I'll tell you the basic concepts of machine learning and deep learning. So what is machine learning? I think that everyone must have heard the phrase machine learning in newspapers or magazines. Then you must also know that machine learning is somewhat related to AI, which is very popular today. What is machine learning? As the name implies, it seems to say that the machine has the ability to learn. Those articles often describe machine learning as a mysterious technique, such that we will get artificial intelligence after machines have learned. Then machines will rule all mankind. So what exactly is machine learning? In fact, machine learning can be generally described in one sentence. What is machine learning? Machine learning is to make the machine have the ability to find a function. After the machine has the ability to find functions, what can it do? It can do a lot of things. For example, suppose you ask the machine to do speech recognition. The machine listens to a clip of audio, then generates the corresponding text. Then all you need is a function. The input of this function is an audio signal, and the output is the content of this audio signal. Then you can imagine that the function that can turn the sound signal into text is obviously very complicated. It is impossible that humans can write down the function by hand. This function is really complicated. Humans have absolutely no ability to write it down. So we expect to rely on the power of the machine to find the function automatically. This is machine learning. The example I just gave is a speech recognition task, and there are many other tasks. The thing in common is to find a complicated function. For example, suppose now we have an image recognition task. What kind of function do we need? The input of this function is an image. What is the output? The output is the content in the image. Take the well-known AlphaGo as an example. In fact, it can also be viewed as a function. In order to make the machine play Go, all we need is a function. The input of the function is the position of black and white on the Go board. The output is the next position the machine should play. Assume that you can find a function. The input of the function is the position of black and white on the Go board. The output is where the next step should be placed. Then we can make the machine play Go automatically. Then we made an AlphaGo. As the output of the function differs, machine learning has different categories. Here we introduce some technical terms. The first term is regression. Regression means the function we are looking for outputs a number. This kind of machine learning task with scalar output is called regression. Here is an example of regression. Suppose what we want the machine to do is to predict the value of PM 2.5 at a certain time in the future. What the machine needs to do is to find a function denoted as f. The output of this function is the value of PM 2.5 at noon tomorrow. The input may be various values related to predicting PM 2.5. It might include the value of PM 2.5 today, average temperature today, and average ozone concentration today, etc. This function can take these values as input and output the PM 2.5 value at noon tomorrow. The task of finding this function is called regression. Are there any other tasks? There are other tasks besides regression. Another task that everyone is familiar with is called classification. The classification task is we would like the machine to do multiple choice questions. Some options are created by humans in advance, also called categories. The output of the function we are looking for is among the options we created. Choose one as the output of the question. This task is called classification. For example, everyone has a Gmail account. There is a Gmail account function that can help the user to detect whether an email is spam or not. The input of this function is an email. What is the output? You must first prepare the options you want the machine to choose. In the problem of detecting spam, there are two possible options, which are spam or not spam, yes or no. The machine must choose an answer, either yes or no. This is the classification problem. Classification problems aren't limited to having only two options. There can also be multiple choices. For example, what AlphaGo does is also a classification task. But its task is different in the sense that AlphaGo has more options to choose from. If you want to train a machine to play Go, or if you want to train an AlphaGo yourself, how many options should you give it? Just think about how many positions there are on the board. We know there are 19 times 19 available positions on the board. So, the task of training a Go playing machine is actually a multiple choice question with 19 times 19 options. What you want the machine to do is to find a function. The function takes all black and white stones positions as its input and outputs the correct choice within the 19 times 19 choices. That is, within the 19 times 19 choices. It outputs the most winning next step. So this problem is also a classification problem. Actually, in many textbooks about machine learning, when they talk about all kinds of tasks machine learning does, they say machine learning's tasks can be separated into two categories: regression and classification. Only those two. But if you thought that machine learning is simply two different kinds of tasks, regression and classification, it's just like you think. There are only 5 continents in this world. You know that the world is not only the 5 continents, right? There is still a land of darkness. Before Demon Slayer was serialized, we had already set off to the land of darkness. And until now, we still haven't arrived yet. From this, we can see that how far away the land of darkness is. So, in the field of machine learning, what is the so-called land of darkness? Outside of regression and classification, there is a problem that people are often afraid of: structured learning. That is, the machine not only needs to do multiple choice questions or output a number, but also needs to produce a structured object. For example, draw a picture or write an essay. This kind of problem, where the machine needs to output structured objects, is called structured learning. Speaking more anthropomorphically, in a fashioned way, you can say that the machine learns how to create. So far, we have talked about the 3 tasks of machine learning: regression, classification, and structured learning. Next, we'll talk about how machines find the function. After all, machine learning is finding a function. So how do they do that? I'm going to use an example here to explain how the machine finds a function. What is the example here? Before telling you the example, I would like to share with you that this course has a YouTube channel. I upload recordings of classes onto this YouTube channel. Thanks to the students who took this course in the past, actually quite an amount of people have subscribed. So I am actually a third-rate YouTuber. My videos don't have that many views, though. But I have more than 70,000 subscribers. So why did I suddenly mention my YouTube channel? Because our example has something to do with YouTube. Do you know what a YouTuber cares about most? A YouTuber cares about the traffic of his channel, right? Suppose a YouTuber makes a living by YouTube. He will care about his channel's traffic, which earns him profit. So I want to ask if it is possible for us to find a function. The input of this function is YouTube's background information, and the output is the total amount of clicks in the next day. If you have a YouTube channel yourself, you may know that in the background of YouTube, you can find a lot of related information. For example, how many people pressed like on each day, how many people subscribed each day, or how many views each day. Can we utilize all the past information to predict how many times it is likely to be viewed tomorrow? Is it possible that we find a function? The input of this function is YouTube's background information of my channel, and the output is the total number of views that this channel will have on the next day. Some of you may ask why I want to do this. If I earn money on YouTube, I can predict how much I will make in the future. But I don't earn money on YouTube. So I actually don't know why I need to do this. It is not even useful for me. I just wanted to give an example. Okay, now we want to know how we can find this function. This function f that we're trying to find takes the data from YouTube's management interface as the input and outputs the total view this channel will get on the next day. The process of finding this function using machine learning can be divided into 3 steps. We will take the task of predicting the number of views on this channel as an example to explain how these 3 steps actually work. The first step is to write out a function with unknown parameters. In short, we start by guessing what function f looks like. What does its formula look like? For example, let's make a very rough guess of what f might look like. What kind of relationship would the input and the output have? We assume it looks something like this. Y equals w times x1 plus b. What does each variable represent, respectively? The y variable represents the total views we will get today. But since today isn't over yet, we do not know the total number of views today. This is something that is unknown to us. Y is the prediction we're trying to make. The total number of views we will get today. Then what about x1? X1 is the number of views that we got on this channel yesterday. This means that both y and x1 are numerical values. Y is the prediction we're trying to make, and x1 is the information given. What about b and w? B and w are unknown parameters that we're trying to find with the help of the data. We don't know what w and b should be. We could only make a rough guess. But how do we even come up with a guess? The guess often comes from your understanding of the nature of the problem, which is domain knowledge. That's why people always say, to use machine learning, you need some domain knowledge. And when is domain knowledge needed? Domain knowledge is needed when we have a function with unknown parameters. So, how do we know that? This function f predicts the number of future views by multiplying the number of views from the previous day by w, and then adding b. We don't know that, it's just a guess. We're guessing that the number of clicks we get today is always somewhat related to the views we got on the previous day. So, we take the number of views from the previous day and multiply it by a value. But the prediction is always not exactly accurate. So we add b to correct it and take the result as our prediction. This is a guess, and it's not necessarily correct. We will come back later to correct this prediction. Anyway, we now guess that y equals w times x1 plus b, and both b and w are unknown. Now we have a function that has several unknown parameters. These kinds of functions with unknown parameters are called models in machine learning. That's why we often hear the word model in the field of machine learning. When we talk about machine learning, a model is some function that has unknown parameters. Okay, so the x1 here is something we know in this function. It is something that we already know. In our case, it is the data from YouTube's management interface. So, we already know how many views we got on the previous day. This is called a feature. As for w and b, they are unknown parameters. Here, we also give w and b different names. This unknown parameter, w, is multiplied by the feature. We call it the weight. This unknown parameter, b, is added directly without being multiplied by the feature. We call it the bias. These are just the definitions of some nouns. As we continue, these technical terms will help us clarify things in the model and make explaining more convenient. So, this is the first step. What about the second step? The second step is to define something called the loss. What is a loss? It is also a function. The inputs of this function are the parameters of our model. I have written out our model, right? Our model is called y is equal to b plus x1 multiplied by w. where b and w are unknown. That is what we are going to find out. As for L, also known as loss, it is a function. What are the inputs of this function? The inputs of this function are b and w. So, L is a function. Its inputs are parameters. It's the parameters of the model. Then, of this loss, of this function, what do the output values stand for? The output values from this function stand for that. If we set these unknown parameters to certain values, how well it performs. It might be a little bit abstract for you to understand. So, I am giving you a concrete example. Suppose that we set the unknown parameters b, the bias, which is equal to 0.5 k, and w, which is equal to 1. How do we calculate this loss? If we set b to 0.5 k and w to 1, then the function we are going to use to predict the numbers of viewers in the future becomes y is equal to 0.5 k plus x1 multiplied by 1. Then, this kind of function, 0.5 k and 1, the function they stand for. How much is it? This thing is so-called loss. Then, in this problem, how do we calculate this loss? We have to calculate it from the training data. In this problem, what is our training data? Our training data is the number of viewers on this channel in the past. For example, the number of viewers from 2017 to 2020 is known on this channel every day. Here are all fake numbers. I made them up. Okay. So, we know that from January 1, 2017 to December 31, 2020, what the number of viewers is. Next, we can calculate the loss. How do we calculate it? We put the number of viewers on January 1, 2017 into this function. We have said that we want to know when b is set to 0.5 k and w is set to 1, how well this function will perform. When b is set to 0.5 k and w is set to 1, the function we use to predict is y is equal to 0.5 k plus x1 multiplied by 1. Then, we will replace the x1 by 4.8 k and see what the predicted result is. So, based on this function, b is set to 0.5 k and w is set to 1. If on January 1st, the number of viewers is 4.8 k, the number of viewers the next day should be 4.8 k multiplied by 1 plus 0.5 k, which is 5.3 k. As for the number of viewers the next day, do we know it on January 2nd? In fact, we know it from the back end. So, we could compare them to know, between the predicted result and real result of this function, how big the difference is. The predicted result of this function is 5.3 k. What is the real result? The real result is 4.9 k. It is overestimated. It overestimates the number of possible viewers on this channel. Then, we can calculate the difference. We calculate the difference between predicted value and real value. The predicted value here is represented by y. The real value here is represented by y head. You can calculate the difference between y and y head to get an e', which represents the difference between the estimated value and the real value. There is more than one way to calculate the difference, actually. Here, we subtract y from y head and take the absolute value directly. The calculated value is 0.4 k. Okay, the data we have now is not only of January 1st and of January 2nd, but of from January 1, 2017 to December 31, 2020. 3 years of data in total. The real value is called label. So, I often hear people saying that machine learning needs labels. Labels refer to the real value. This is called label. Also, not only can we use the value of January 1st to predict that of January 2nd, but we can use the value of January 2nd to predict that of January 3rd. Suppose our current function is y is equal to 0.5 k plus 1 x1. As for January 2nd, according to the views on January 2nd, what is the value of predicted views on January 3rd? It's 5.4k. Replace x1 with 4.9k. Multiply it by 1, and add 0.5k. We get 5.4k. Next, calculate the gap between 5.4k and the real answer, also known as the label. The label is 7.5k here. So, it seems to be an underestimation. We underestimated the views of this channel on January 3rd. So we calculate E2. This E2 is y minus. It's the gap between y and y hat, which is 2.1k. Hence, with the same method, you can obtain the prediction error of each day during the past 3 years. Now, suppose our function is y equal to 0.5k plus 1x1. The error of each day in the past 3 years can be calculated entirely. The error of each day gives us a small e. Okay, then we will sum up all the errors of each day and get the average from the summation. This big N represents our number of training data points. The number of them is the number of those training data for 3 years. So, it's 365 times 3. 365 days a year, 3 years, so it's 365 times 3. Then we get an L. We calculate the big L. This big L is the result of summing up these E's, which are the errors of all training data, making up our loss. The bigger the big L is, implying the worse this set of parameters is. The smaller the big L is, implying the better this set of parameters is. As for this E, which is the difference between the estimated value and the actual value, can be calculated by different methods actually. In our example just now, we calculated the gap between y and y hat in absolute value. With this method of calculating the gap, this big L obtained. The loss obtained is called mean absolute error, whose abbreviation is MAE. In homework 1, instead, we calculate the square of y minus y hat. If your E is calculated by the square of subtracting y's today, it is called mean square error, also known as MSE. In fact, there are very subtle differences between MSE and MAE. Usually, you have to choose which is your method to measure distances. That depends on your needs and your understanding of this task. We won't go into detail here. Anyway, we choose MAE as the way we calculate this error. Adding up all the errors, you get the loss. It's your freedom to choose MSE, and we will use MSE in homework 1. Also, there are some tasks in which y and y hat are both probabilities, both probability distributions. At this moment, you may choose cross entropy. We'll talk about this later, too. Anyway, we choose MAE here. This is the second step of machine learning. Those numbers I just mentioned didn't come from a real example. But, in this course, when I give a lecture, I am here to show you a real example. Therefore, the following numbers did come from a real example. It's the calculated result from the real background data of this channel. We can adjust different W. We can adjust different B. Seek all different W's and all different B's exhaustively, and combine them. We can try different combinations of W and B and calculate their losses. Finally, you can draw the contour map below. On this contour map, the redder it is, the greater the loss calculated is, implying the worse this set of W and B is. The bluer it is, indicating the smaller the loss is, implying it's a better combination of W and B. Take this combination of W and B, put it into our function, into our model, and then we will predict it more accurately. So you know that, suppose W is minus 0.25 and B is minus 500. It means that this W is minus 0.25 and B is minus 500, which means that there are fewer and fewer people watching this channel every day. And the loss is so big, which doesn't match the real situation. If we substitute W with 0.75 and substitute B with 500, the correct rate or the estimation will be more accurate. The most accurate estimation seems to be here. If you substitute W with a value very close to 1, and substitute b with a small value, such as around 100. At this time, the estimation is the most accurate. This may be closer to everyone's expectation that you take the total number of clicks in the previous day to predict the total number of clicks on the next day. Maybe the total number of clicks on the previous day and the number on the next day are almost the same. So we substitute w with 1 and substitute b with a smaller value. Maybe your estimation will be quite accurate. A contour map like this is that you tried different parameters and then calculated its loss and then drawn the contour map, which is called error surface. This is the second step of machine learning. Next, we move on to the third step of machine learning. What we do in the third step is to solve an optimization problem. It doesn't matter if you don't know the optimization problem. What we are going to do today is to find a, w, and b. Find a value of unknown parameters to see that which value can make our big L, can make our loss value be the smallest. That is the w and b we are looking for. The w and b which can make the loss smallest are called w star and b star, which means that they are the best set of w and b to minimize the value of the loss. So, how to do this? The only one optimization method that we will use in this course is called gradient descent. How to use gradient descent? How to use this method? It is done like the following. To simplify, let's assume that there is only one unknown parameter, w. Let's assume that there is no unknown parameter, b, only the unknown parameter, w. When we substitute w with different values, we will get different losses. And this curve is the error surface. In the previous example, the error surface we saw is two-dimensional, it's 2D. There is only one parameter here, so the error surface we see is 1D. Then how to find a w to minimize the value of this loss? First, you have to randomly select an initial point. The initial point is called w0. The initial point is often randomly selected. Just pick one randomly, really random. Later in this course, we will know that there may be some methods that can give us a better value of w0. Here, we don't talk about it. We just treat it as random. Randomly roll a dice to decide the value of w0. Let's assume that the result of our random decision is at this place. Then, you have to calculate the derivative of loss with respect to w. When w is equal to w0, I assume you know what differential is. This is not a problem for you. Calculate the derivative of loss with respect to w. If you don't know what differential is, that's okay. What we are doing is to calculate the slope of this error surface at this point, at the point of w0, which is this blue dotted line. What if the slope of this dotted line is negative? What does that mean? It means that the left side is higher, and the right side is lower. Around this point, the left side is higher, and the right side is lower. If the left side is higher and the right side is lower, what are we going to do? If the left is higher and the right is lower, then we increase the value of w to make the loss smaller. If the calculated slope is positive, it means that the left side is lower and the right side is higher. It looks like this. The left side is lower, and the right side is higher. If the left is lower and the right is higher, it means we need to make w smaller. If you can reduce the loss value by moving w to the left, you should make w smaller. Even if you have no idea what slope is, it doesn't matter. Just imagine that there is somebody standing at this point, looking around. This means taking the derivative. The derivative helps us know whether the function will have a lower value at the right or the left to the point where we are. Then we take a step towards the point with a lower function value. How big is this step? The size of this step depends on two things. The first is how big the slope at this point is. The greater the slope, the bigger the step is. If the slope is small, our stride will be small. In addition to the slope, namely, the derivative, which we just talked about. In addition to the derivative, there is another thing that affects the step size. We denote it with eta. This eta is called the learning rate. The rate at which the model learns. Where does it come from? It depends on you. You can decide the value of eta yourself. If eta is set larger, the amount of parameter update will be larger, and the model will be able to learn faster. If eta is set smaller, the rate of the update will be slower, and the parameters will have slight changes at each iteration. Things that need to be set manually when practicing machine learning are called hyperparameters. The first step of machine learning is to define a function with unknown parameters. And these parameters, the unknowns, will be found by the machine itself. Oh, there's a question. Please speak up. Okay, this is actually a good question. Let me repeat it. Someone asked why a loss function can have negative values. The loss is a user-defined function. So from the definition we just made, the loss here is the absolute value of the difference between the ground truth value and the prediction. According to the definition now, it cannot be negative. But the loss function is up to you. Say, if the loss function today is the above-mentioned absolute value minus 100, then it may have negative values. I have to remind you about the curve here. It is not of any real loss functions. It's a random curve from the internet as an example. The reason is that I want to give a more general example. It is not an error surface from any real tasks. So this loss curve, this error surface, can have any shapes. There is no presumption regarding the shape of a loss curve. But from the definition of the loss here, it cannot be negative, since it outputs absolute values. But the loss, because this function is up to you, it may be negative. Since someone raised a question here, we should pause for now. See if you have any questions. In the future, the TAs will help me watch the live stream on YouTube. Please read out the questions during the live stream for me, if there are any. Help me read those questions. We will first move on with the session. Until the session comes to an end, we will answer those questions. I'll ask again. Does any of you have questions here? Great. If not, please let me continue. Okay, where were we? We just talked about hyperparameters. They should be set manually. So in machine learning, those you have to set manually are called hyperparameters. We say we are gonna move W0 one step to the right. Then this new position is called W1. The step size is eta multiplied by the differential. To express it in a mathematical formula, it is W0 minus eta times the derivative, which is W1. Then, you just repeat the operation done before. Calculate the differential of W0. And then decide how far to move W0. Then move it to W2. Then you continue to do the same operation over and over again. Keep moving the position of W. In the end, you will stop. When will it stop? There are often two situations. The first situation is that you lost patience. In the beginning, you will set up a limit. When you are adjusting your parameters, calculating differentials, I only calculate limited times. You might set the upper limit to 1 million times. Hence, after updating the parameters 1 million times, I won't update them anymore. As for how many times I should update, this is also a hyperparameter. This is up to you. If the deadline is tomorrow, you may update fewer times. You may set it up a little more if the deadline is next week. There is another ideal stopping situation. When we keep adjusting the parameters, we arrive at some places where its differential, which is this term, exactly equals 0. If this term is exactly 0, 0 times the learning rate eta remains 0. So your parameters will not move their position anymore. Suppose we are in this ideal situation. We update W0 to W1, and then update it to W2. In the end, we update it to WT with a bit stuck. We stuck at WT. That is, the differential is 0. The position of the parameter will not be updated anymore. On this point, you might find out that gradient descent has a huge problem. This huge problem in this example is obvious. That is, we do not find the real best solution. We don't find the W, which can minimize the loss. In this example, by setting W to this place, you can minimize the loss. However, if gradient descent starts from this place as a random initial position, the training is likely to stop. When you arrive here, you can't move the position of W anymore. This position, this is really the place where loss is the smallest. It is called global minima. This place is called local minima. The loss of its left and right sides are a bit higher than itself. But it is not the lowest point on the entire error surface. This thing is called local minima. So you may often hear someone saying that gradient descent isn't a good method. This method has the problem of local minima. There is no guarantee to find the real global minima. But textbooks often say this. Content farms often say this. But this is actually just an illusion. In fact, if you have done something related to deep learning, or you have trained your own network, or you have done gradient descent by yourself, local minima is actually a non-issue. When we were doing gradient descent, the real problem we confronted is not local minima. Then what is it? We will talk about it later. Temporarily, you just believe what most people say. Gradient descent has a problem with local minima. In this example, it is obvious that there is a local minima problem. But later, I will tell you what gradient descent's real pain points exactly are. The things mentioned above is an example with only one parameter. Actually, our model has two parameters, W and B. How to use gradient descent under the situation of two parameters? In fact, it is no different from the situation of a single parameter. If you have no problem with one parameter, you can quickly generalize to two parameters. We have two parameters now. Then we give it two parameters. We give them random initial values, W0 and B0. Then what's next? You have to calculate the differential of loss with respect to W. You have to calculate the differential of loss with respect to B. Calculate at the position where W is equal to W0, where B is equal to B0, where W is equal to W0, where B is equal to B0. You have to calculate the differential of L with respect to W. Calculate the derivative of L with respect to B. After calculating, according to the method that we have just used, with one parameter, we update W and B. Subtract the learning rate from W0. Multiply the result of the differentiation to get W1. Subtract the learning rate from B0. Multiply the result of the differentiation to get B1. Some students might want to know how to calculate this differentiation. If you can't calculate the differentiation, don't be worried. Why don't you be worried about it? In the framework of deep learning, or in our homework 1, with the package PyTorch that will be used, the calculations of differentiation are automatically calculated. You can write only a line of code, and the results of the differentiation would be calculated automatically. Even if you don't know what you are doing, you can still get the results of the differentiation. Here, even if you don't know what differentiation is, don't worry. This step can be done in one line. When doing homework 1, you can try it by yourself. Repeat the same procedures. Keep updating W and B. And expect that at the end, you can find the best W, W star, and the best B, B star. Here is an example. We would show everyone that suppose on this question. How we do it. Suppose that you choose a random initial point here. First, you calculate the partial derivative of L with respect to W. And calculate the partial derivative of L with respect to B. Then you update W and B. The direction of the update is the partial derivative of L with respect to W, multiplied by eta and added a negative sign. And the partial derivative of L with respect to B, multiplied by eta and added by a negative sign. After calculating the derivatives, you can decide the direction of the update. You can decide how to update W. How to update W. Combining the update directions of W and B, we can get a vector, which is this red arrow. We move from this position to this position. Then calculating the derivatives again, you can decide which direction to update. After multiplying the values of partial derivatives by the learning rate, and adding a negative sign, you can know where the red arrow will point. You can know how to move the positions of W and B. Keep moving and moving. Expect that you can find a good pair of W and B in the end. After using gradient descent and doing some calculations, we get the actual result. The best W calculated by us is 0.97. The best B is 100. It's very close to our guess. Because the value of X may be very close to Y. This W is set to a value close to 1. And B is set to a relatively small value. How big is the loss? The calculated loss is 480. That is, on the data from 2017 to 2020. If you use this function, setting B to be 100, and W to be 970, the average error is 480. This means that the error of the predicted number of views is about 500 times. Until now, we have talked about the 3 steps of machine learning. First, write a function. There are unknown parameters in this function. Second, define a function called loss. Third, solve an optimization problem. Find a pair of W and B to minimize the loss. The values of W and B found just now can make the loss as small as 480. But, is it a satisfying or commendable result? Maybe not. Why? Because the procedure of these 3 steps is called training. We are now using the data with known answers to calculate the loss. Data from 2017 to 2020 are those we have already known the answers to. We have already known that from 2017 to 2020. How many views per day? So, in fact, we are just getting hyper by ourselves. Just pretending we don't know the number of views on the next day. We use this function to make predictions, finding that the error is 480. But, is the number of views that are already known what we really care about? No. What we really care about are the things we don't know, which is the number of views in the future. So what are we going to do next? We will take this function and use it to predict the number of views in the future. Here, we only have data from 2017 to 2020. On the last day of 2020, New Year's Eve, we found this function. Starting from the first day of 2021, we apply this function to predict the number of views on the next day. We use the number of views on December 31, 2022. Predict the number of views on New Year's Day in 2021. We use the number of views on New Year's Day to predict the views on the day after New Year's Day, which is January 2nd. Use the number of views on January 2nd to predict the views on January 3rd. We do this every day until February 14th, until Valentine's Day. Then we get the value for the average error. What is the average error? This is the result of real-world data on 2021's data which has not been seen before. This error, we denote it as L prime, is 0.58. So on data that have been seen, on training data, the error is relatively small. On data that have not been seen. On 2021's data, it seems that the error is larger. So our average error per day is about 580 people. Around 600 people. Can we do better? Before we do anything, let's analyze the results first. How do you interpret this graph? The horizontal axis of this graph represents time. So the leftmost point at 0 represents January 1, 2021. The rightmost point represents February 14, 2021. The vertical axis is the number of views in thousands. What does the red line represent? The red line is the actual number of views. The blue line is the number of views predicted by the machine. Using this function, you can see very clearly that there is nothing magical about this blue line. It's almost the same as shifting the red line to the right by 1 day. It didn't really make any powerful predictions. It simply shifted the red line to the right by 1 day. This is reasonable, because we think the relationship between x1, the number of views on the previous day, and the views on the next day. How did we use the number of views on the previous day to predict the number of views on the next day? We multiplied the number of views the day before by 0.97. Then plus 0.1k, plus 100, and obtain the number of views on the next day. So you will find out that the machine almost just took the views from the previous day to predict the views on the next day. But if you look closely at this graph, you will see there's some special phenomenon in this real-world data. It is periodic. It has an interesting periodicity. Do you know what the pattern is? The views become very low for 2 days every 7 days. 2 days when the views are very low. What days are those 2 days? I found out that those 2 days are fixed. They're Fridays and Saturdays. I can understand on Friday and Saturday. Everyone will go out because it's the weekend. Who needs to learn machine learning? Who wants to learn machine learning on Saturday? But I don't know why. Everybody goes to learn machine learning on Sunday. I haven't understood why this happened. Maybe it's because of YouTube's magical algorithm. For instance, YouTube will recommend videos. Maybe when YouTube is recommending videos on the channel, it chooses not to recommend them on Fridays and Saturdays, but only on Sundays through Thursdays. But why on Sundays through Thursdays? I haven't understood that either. But anyway, when we look at the results, it's like this. A cycle every 7 days. Every Friday and Saturday. There are very few people watching. Since we already know that every 7 days is a cycle, this formula, this model, obviously sucks. Because it can only see the day before. If the cycles occur every 7 days, we should look at 7 days at once, right? Suppose we have a model. It refers to the data from the previous 7 days. It copies the data from the previous 7 days as the predicted result. Maybe the prediction will be more accurate. So we have to modify our model. Usually, the modification of the model often comes from your understanding of this problem, which is domain knowledge. So, in the beginning, when we don't understand the problem at all, we just write 1 randomly. Y is equal to b plus wx1, which doesn't perform very well. Next, after observing the real data, we conclude that there is a cycle every 7 days. So we should take views in the first 7 days into consideration. Thus we wrote a new model. What does this model look like? This model is that y is equal to b plus xj. What does xj stand for? This subscript j represents how many days ago. This j is equal to from 1 to 7. That is, from 1 day ago, 2 days ago. Continue to 7 days ago. For all the data in these 7 days, we multiply them by different weights. That is, we multiply them by different wj. Then we add them up. And plus bias to get the predicted result. If this is our model, what is the result we got? Our loss on the training data is 0.38k. That's because here we only consider 1 day. Here we consider 7 days. So on the training data, you will get a lower loss. Here we consider more information. So you should get better on the training data. That is, you have a lower loss. Here the loss is 0.38k. But on the unseen data, can the model do well? On the unseen data, it is better. The loss is 0.49k. So if only consider 1 day, the loss is 0.58k. While considering 7 days, the loss is 0.49k. For every W and B here, we all use gradient descent to calculate its optimal value. What does its optimal value look like? We show it here. We show you what its best value looks like. Of course, I can't fully understand the logic of the machine. I thought it would select data from 7 days ago. Copy the number of viewers 7 days ago. Directly. I don't think it selects like this. Its logic is that the previous day has a lot to do with the value of the next day you want to predict. So W1 star is 0.79. I don't know why it's still considered the previous 3 days. The W for the previous 3 days is 0.12. The W for the previous 6 days is 0.3. The W for the previous 7 days is 0.18. But it knows. If it is the previous 2, 4, or 5 days, its value will be inversely proportional to what we have to predict in the future. So for W2, W4 and W5, their optimal values, which let loss on the training data be 0.38k, is negative. While W1, W3, W6 and W7 are positive. We consider the value of the previous 7 days. Then you might ask, whether it's possible to consider more days? Yes, it's possible. We can make an easy change to consider more days. Originally, we considered the first 7 days. Then what happens when considering 28 days? 28 days are equal to a month. We use the number of people watched each day in the previous month to predict the number of viewers the next day. What is the predicted result? The loss on the training data is 0.33k. On the 2021's data, the loss is 0.46k on the unseen data. The performance looks better in 28 days. Okay, then what will happen when considering 56 days? The performance is slightly better on the training data. The loss is 0.32k. The loss is still 0.46k on the unseen data. It looks like that. There is no way to make more progress when considering more days. It seems that considering the number of days has reached its limit. Okay, for these models here, they all take the input x. Do you remember what x is called? It's called a feature. We multiply the feature by weight and add a bias to get the predicted result. Such models have a common name, called the linear model. Next, we will see how to make the linear model better.